Let's get started. Welcome back. So, I threw up here just to remind you of our definitions. So I just want to continually remind you of these three fundamental definitions of algebraic spaces: the Lie-Mumford stacks and algebraic stacks. And then remind you that what we did last time was we showed that these definitions actually imply that the diagonal is representable. This is the main theorem from last time, that the diagonal of any algebraic space is representable by schemes, and that the diagonal of an algebraic stack is just representable. And then this allowed us to finish this algebricity of quotients theorem here in the bottom. We'd already done some of that, I guess, 2 times ago, but now we can take quotients of smooth groupoids, Étale groupoids, and Étale equivalence relations. And what's next up is, and what I'll cover today is sort of getting into like properties of algebraic stacks. In the geometry of algebraic stacks, we're going to define notions of dimension, tangent spaces, and residual gerbes. Let's get started. Well, maybe before, I'll just take some, I can take questions if there are any. Okay. So recall that, so dimension is a tricky subject in algebraic geometry. Even in just scheme theory, it takes some time to develop the basic properties. If we have a scheme, the dimension of it is the dimension just of the underlying topological space. That's the Krell dimension. And there's also this local dimension as well, which is the minimum over all open neighborhoods containing your point. And this is sort of necessary because there's pathological, like in general, your scheme may not be pure dimensional. I mean, what to think of is you might have sort of multiple components. And then if your point is here, you don't want to say it's locally dimension 1 around that point. And so what we would like is a corresponding notion for stacks. I mean, the definition's on the right-hand side, but we can't just, even though we have the underlying topological space of an algebraic stack, we don't want to use that as its dimension. And we'll see maybe later why. I mean, an example we'll think of is just BG, which is just one point. Instead, we want to use, basically, the goal is we want to define the dimension of an algebraic stack using a presentation. So like if you have a smooth presentation, X, like I will just put this in quotes, but this is essentially the definition, although we just have to be careful, is that this should be the dimension of U minus the relative dimension of this map, of the smooth map. Right, okay, so let's get into the specifics here. I have the definition on the right-hand side. We take, so I need to first define it for algebraic spaces, and I'm only going to restrict to the Noetherian setting. So if I have an Noetherian algebraic space and a point, I just take a Étale presentation and I define the dimension as the dimension of that Étale presentation. And this is all fine. It's well defined because Étale maps have relative dimension 0. Great, and now we can then use that. I mean, we need to define the notion first for algebraic spaces because we're working with very general algebraic stacks whose diagonal might only be representable by algebraic spaces and not schemes. So here we take an algebraic stack and a point, and we choose a smooth presentation, and you can consider the corresponding groupoid. Maybe I'll write this over here. So we have X is our algebraic stack, we have U over it, and we choose a pre-image. And then if you take this fiber product, this is R, right? And that's your smooth groupoid corresponding to that choice of presentation. And you also have this identity section here, E. So you can consider E of U. Whoops, that's not E of U as a point in R, and right, it's over under both projections, it maps to U. And I can also consider the fiber over U here under, let's call this map, yeah, this is S and this is T, and let's call RU, this is the pre-image under T. And yeah, so then we define the dimension just to be the dimension of U minus the relative dimension, meaning the dimension of the fiber RU at E of U. Okay, that's our definition. What we need to show is that it's well defined. But once that's true, once you show that, then you can define sort of the global dimension as the supremum of all the local dimensions. So this is unlike the case of schemes where you first define global dimension and then local. Here we've gone the other way. Okay, so what I owe you is a proof of this. I do want to give some details or some indication of why it's true. Like I think I don't think the details in this case are so inspiring. So I'm going to go quickly here. But it's really one of those cases where it's better done on your own, and just because a lot of these things are subtle. And so I've sort of cheated and wrote down sort of a sketch of a proof for why it's well defined. And so up here I have the same setup I wrote before, right? And then this local dimension is defined as this difference. And what I want to argue is that it's well defined. And there's basically one fact about dimension that we'll use is that if you have a smooth morphism of schemes, so you have a smooth morphism of schemes, and you have a point X mapping to Y, then the dimension of the total space, whoops, that's the eraser. The dimension of the total space is the dimension of the base plus the dimension of the fiber. Okay, and so we in order to show that it's independent, we choose another presentation, and then we have a corresponding groupoid R prime, and we can also choose a U prime going to an X, and here we might have a point U double prime mapping to U prime and U. And by symmetry, it suffices to show that basically we're trying to show that this dimension is independent, this difference is independent of the choice of U. So by comparing U and U prime to U double prime, it suffices to show this equality at the bottom. And right, so in order to show that, we can sort of consider, we want to apply this geometric fact, and we consider sort of this fiber product diagram. So we have our three different presentations here, and so we're going to apply, and maybe we note that this fiber here is equal to, just because this is U prime over X. So if you consider what our setup was, this was in our notation, this is the same as R prime U prime. And so we apply the fact to this smooth morphism, and what that just tells you, the fact just tells you that you get this equality, but we can but because we have that this identification of U double of the fiber of like U double prime U, we can we then get this equality. And if you note that in this second equality here, there's two terms that are the same as in this one, namely, so I could substitute in for the dimension of u minus the dimension of u double prime. And so what we see is it actually suffices to show this equality. And for that, it's actually, yeah, that's not so hard. So here, just for simplicity, I just assumed that all of these points have the same residue field. Yeah, and in general, it works because the dimension is insensitive to field extension. And then, so if you consider this Cartesian cube, and you look at just the back square, you have a fiber product square, and then you use, and these are all like smooth and finite type over a field. And so, so you have the additivity of dimension. Anyway, that was really quick, and yeah, but I don't think, yeah, as I said, I don't think it's that interesting. So I don't want to really dwell on it. Yeah, I'd rather discuss examples. So essentially from the definition, if you have a smooth affine group scheme and you have an action on another scheme, U, on a K scheme, then the dimension of the quotient is just the difference between the dimension of U and the dimension of G. And so for in specific examples, the dimension of BG is equal to negative of the dimension of G. So like the dimension of B of GM is -1. So we are in the world of negative dimensional geometric objects. And on the other hand, if you take, A1 mod GM, then you have something one-dimensional acting on something one-dimensional. So you get something zero-dimensional. And, similarly, say if I just take A2 mod GM with the scaling action, then it's one-dimensional. And this sort of makes sense because, inside here, you have a copy of P1. But something that's tricky in this example, it'll show up later, is that you also have this closed substack, and it's codimension 2, which also makes sense because, yeah, this has dimension -1. And now if you try to think about MG, can we compute the dimension of MG yet? We had this description of MG as a quasi-projective variety mod PG, some PGLN, where this was some locally closed piece of the Hilbert scheme. In some Hilbert scheme of like tricanonically embedded curves. And so this does tell you that the dimension of MG is the dimension of H prime minus the dimension of the group. And you could try to use deformation theory to compute these things, maybe just to show that the Hilbert scheme is smooth, and then compute its tangent space. But we're actually going to follow a different way. So I'm not going to compute the dimension right now. We're going to wait until we know that it's smooth, and then we'll compute the dimension of its tangent space. And so rather than working with the Hilbert scheme, we'll just work directly with the stack. So yeah, we're going to return to this later. Right, so that's my quick survey of dimension. Are there questions?
Yes, I have a question. So, do we know that all algebraic space come from some? So yeah, can you take the first page? Can you go back to the first page?
Oh, sure. Yeah. The very first page. Mm-hmm.
Okay. No. The second page. Thank you. Sorry. Okay. Do we know that all algebraic spaces come from some R and U?
Some R and U, yes. Right, because right. But because by definition, any algebraic space has an étale presentation. Right. So yeah, if X is an algebraic space, you can take an étale presentation, and because this is representable by schemes, the fiber product is also a scheme. And then, you know, I showed that there exists a U mod R last time. And the fact is that, yeah, if you start with X in a presentation and build the corresponding étale equivalence relation, and then take the quotient, you get back what you started with. Does that help?
Yes, thank you.
And this is the same if we take a stack and a smooth presentation?
Exactly. Well, yes, except that if this is a stack instead, we don't know that your smooth presentations are representable by schemes. So this R here might then be an algebraic space, and it's possible, but we have not yet. We can't take a quotient in that setup yet. We only define the quotients of smooth equivalence relations of schemes. You can extend that in the case where R is an algebraic space, but I'm avoiding this.
Okay, but then I suppose when we take the fiber RU in this definition too, then this is a scheme. So it should be still well defined.
Well, I think this is in general, this is just an algebraic space. So that's why I needed to define the dimension of an algebraic space first to make sense of this.
Okay, sorry, I got confused because wouldn't R to U be representable by schemes then? No, not necessarily.
No, not necessarily. Yeah.
Okay, I see. Thank you.
So since we're dealing with negative dimension, is there any geometric picture that we should be?
Yeah, that's a good question. How do you view this geometrically? Yeah, I don't know. Yeah, I don't know. I mean, my picture of BG would just be a point, but you sort of remember G. But yeah, like in topology, they have other ways to view like these classifying spaces, and then they're not negative dimensional, but infinite dimensional. But like,
No, I got it. Thank you. Because I did attend a talk, and they have I think a simpler definition of BG in topology. So I get by that.
Okay, let's move on now to tangent spaces. And we're going to follow sort of, we're going to define this a risky tangent space of a stack, and we're going to use the dual numbers. So here we fixed a point, a k point. So we have a map from spec k to x. And we just defined the Zariski tangent space formally as all maps from the dual numbers that extend this choice of object. But because we're working with stacks, we need to be a little careful. These are really two commutative diagrams. And you need to mod out by isomorphisms over the dual numbers. Right. So this defines it as a set. And unlike like in the case of schemes, you can define the tangent space differently, right? Because if you have a point, you have a local ring, you could look at the maximal ideal, and then you could take n mod m squared or its dual, and that you clearly get a vector space, and then you show that there's an identification with maps from the dual numbers. In this case, we're just using the dual numbers to define it, so it's not so clear what the vector space structure is. And so here I explain how to get first scalar multiplication, and then we'll move on to addition. Scalar multiplication is easier. You simply, like, if you have a tangent vector tau, so that's tau, and you have some scalar c, and then all you do is you precompose by just by scaling epsilon by c. Now, it's an interesting exercise to check, even in the case of schemes, that this is the corresponding vector space structure to m mod m squared. But unfortunately, addition is a little trickier. So what we're going to use is this equivalence, and this is like it's not easy. This is not easy. But one way to think about this is that I have sort of a diagram where I can include into the dual numbers right? And then the corresponding maps of rings are surjections. And I could take the fiber products of rings, not something you usually do, but you can. And then you have, if you take the fiber product of rings here, what this algebra looks like is just, it looks like two tangent vectors glued together. And what you need to show is that this is a push out it's pushed out in the category of algebraic stacks. Yeah, this takes work. But I think in the case of affine diagonal, I think that's the case I wrote in my notes. It's not too hard. It still takes some work. And what that means is that if the push out, it means that if you have, I'll use a different color, like a map to some other algebraic stack X, to some algebraic stack X, and an isomorphism here, there exists a unique map. And another way to phrase that push out property is exactly, this equivalence here. And so I view that equivalence as a push out property, and then, but it's also, kind of sort of important to point out that this type of equivalence naturally shows up in deformation theory in terms of, in like local deformation theory. It's like one of the first axioms in Schlesinger's axioms in order to get to get a representable hull of a local moduli functor. And it turns out, and this is sort of part of a package. Maybe I'll say a word later, but this is sort of a part of a package that builds up to Artin's criterion, which gives you like specific local criterion to check that an algebraic stack, that a certain stack is algebraic. And this is one of the first like homogeneity properties. But in any case, you can just check that this holds for an algebraic stack, and we're going to use this to define addition. And it's essentially what we do is, what you do is you have, in order to add two tangent vectors, so if you use this equivalence, right, because, okay, so in this equivalence here, you have tau 1, alpha 1, and then a tau 2, alpha 2 on the right hand side. So that using the equivalence, you therefore get this map here. Oh, sorry, you get this map here. And then we sort of, and then you just add the tangent vectors. Where both, maybe I should write it this way, on algebras, epsilon. Okay, and so this gives you a vector space structure. And so what I tried to outline was this proposition here. And it's true more generally without this affine diagonal condition, but as I was saying, the push out property is a lot easier with that hypothesis. And maybe as an exercise, I want to say that this tangent space is naturally an algebraic representation of the stabilizer group, where at least set theoretically, that if you have, suppose you have an element of the stabilizer, and then you have a tangent vector, then you act essentially by pre-composing your isomorphism with G. Right. In other words, to think of G itself is just, you can think of G itself as giving you like a 2 isomorphism between like the map X, the object X, and you just, and alpha was this 2 isomorphism between these other maps, and you just precompose with that 2 isomorphism. All right, I think turning to examples is useful. So I'm gonna go through a couple examples. So let's take G to be smooth and affine, algebraic group. And I'm going to take X to be just the canonical cover of BG. And then because G is smooth, the tangent space is trivial. Or maybe, or if you like, just think for a moment that K is algebraically closed, right? Then this map corresponds to the trivial G torsor, and then there's this, and then then there's this fact that every G torsor over the dual numbers is also trivial, because with smooth groups they're trivializable in the tau topology, and there's only any tau cover of the dual numbers is just like a disjoint union of copies of the dual numbers. And so therefore we see that every extension of the trivial G torsor to the dual numbers is also trivial. So that means that this tangent space is 0.
Can I ask a question?
Yes.
I guess maybe we don't have a good notion of smoothness that lines up this way, but sometimes we think about smoothness as meaning like the tangent spaces are the right size. And so for these negative dimensional things, it seems like this will never be true.
Yeah, that's a good question, Gabe. I'm gonna, with my next example, this will show up. So yeah, I'll address that.
Great, thank you so much.
So yeah, let's take A1 mod GM, and you can consider 2 different points here, right? Remember, this is an algebraic stack whose underlying topological space has 2 points, one open and one closed. And in fact, the open point, this is an open immersion, and then you have the complement of that is a closed stack BGM. But I can take a cover of that, and then this is, let's call this point 0. The tangent space, let's call this stack X, of X at 1. Well, it should be, this is an open immersion. So certainly, it's equal to spec K. So it's 0 dimensional. The tangent space is identified with the tangent space of spec K at the unique point, which is 0 dimensional. But on the other hand, the tangent space at the origin is 1 dimensional. Just because A1 is 1 dimensional. And note that here that the stabilizer of G1 is just trivial, and it acts trivially here. But the stabilizer of the origin is GM, and that acts here. So as Gabe was sort of saying, that like we haven't defined smoothness, but this is an example of a smooth stack of dimension 0. And what we're seeing is that the dimensions of the tangent spaces are not constant. They jump up, but when the dimension of the tangent space jumps up, so does the stabilizer. So it's like the difference between the dimension of the tangent space and the dimension of the stabilizer is constant as long as you have a smooth algebraic stack, and with smooth stabilizers. And maybe as another example of what can go wrong in characteristic P, and when you don't have smooth stabilizers, is you can look at B mu P over field K, say a positive characteristic. And we have this cover. Note that we don't actually know it's algebraic because we haven't taken quotients. We're not taking quotients by flat group schemes. But actually this argument I'm going to say right now will show you how to, will give you a way to actually show that it is algebraic. So I want to argue that the tangent space of B mu P at this point X is actually one-dimensional. So yeah, this corresponds to the fact that mu P, there are, not all G bundles are trivializable in the Étale topology. You have non-trivial deformations of the trivial torsor over the dual numbers. But yeah, one way to think about this is mu P is the quotient of the multiplication by P map. So it's this exact sequence like this. And whenever you have a short exact sequence of groups, you can realize, the classifying stack of the first one as the quotient of this action. So actually B mu P, you can view it as GM mod GM, where the action is by taking T goes to T to the P. And so this gives you a way, at least we know that this is an algebraic stack because this, and this gives us a smooth presentation of B mu P. But also with this presentation, you can compute its dimension. And this tells us that the dimension is 0. So sort of a weird example, topologically, you have the stack B mu P, which is just a point. It actually is a smooth algebraic stack of dimension 0, but it has a one-dimensional tangent space. Okay, let's get to a more geometric example. Let's do it. Let's turn to MG. And let's do G at least 2. And so we're going to fix a curve here where C is a smooth projective connected curve of genus G. And first I'm just going to retranslate what the definition of this tangent space is. Well, well, by definition, it's just all extensions. Modular isomorphisms. And this, if you think about what this is, this tau is then a family of smooth curves over the dual numbers. And such that the central fiber is isomorphic to the curve you start with. And again, modding out by isomorphisms of the total family. And here we're going to now just use a fact. It's actually not a very hard fact, but it's worth a lecture in itself to discuss. Is that you can use, this is a fact from infinitesimal deformation theory. Is that you can identify this with H1C of TC of the tangent bundle. And so this gives us a way to compute it. We just need to compute the tangent bundle. And okay, so H1 of the tangent bundle, we could use Serre duality. So this is saying is H0 of C. The curve is one-dimensional, so this is just the dual of the dualizing sheaf. And the Serre duality tells me this is the same as the sheaf of differentials, or the dualizing sheaf, tensor 2. And because this is positive, because the genus is at least 2, there's no H1 here. So we can use Riemann-Roch to compute this. there's no, okay, let me not write that. There's no H1, and then Riemann-Roch tells me I take the degree of this. So I have 2 times the degree of the canonical, which is 2G minus 2. And then I need to subtract a G minus 1. And so I end up with 3 copies of G minus 1. So we get that the dimension of MG, yeah, so we compute the dimension of the tangent space of MG at any smooth curve is 3G minus 3. And so this is very close to knowing that the dimension itself is 3G minus 3. But we're going to wait until we discuss smoothness.
Can you explain in the second example, A1 mod GM, how you saw the dimension was 1 at the origin? Because like it's not enough to just know A1 has dimension 1, because that's also true at the other points, right?
Yeah, that's a good point. I didn't prove that. Let's see. I fear I'm not going to get be able to come up with a great explanation on the spot. I mean, this is related to something that's going to show up later. Is that in fact the map from A1 this is sort of a mini-versal deformation in that it induces an isomorphism at the tangent spaces of this cover. But that's but I need to show that. I guess it's clear. Okay. I don't think it's that hard, but I don't think I'm going to find the most succinct explanation on the spot. Any other questions I can't answer?
Yes, sorry, I have another question concerning 3. So are we using here, like we are probably using that we are on the état side here right now. Otherwise, this sequence is probably not exact, right? Because we are having like Henselian rings or something like that, such that this map is surjective.
Oh yeah, right. This is only right. Okay. Yeah, I didn't want to get into this. Sorry. Yeah, you need to use the flat site for both BMUP and for these exact sequences. And right. Let me not really get into that because I haven't. I'm giving these examples for BMUP because I think they're worthwhile to keep in mind, but we're not developing the foundations because we don't even know it's an algebraic stack. No, yeah, it's a fair question, right?
Yeah, I think just on the small and big état side, this works.
Which works? What works?
That the sequence is exact.
You needed the flat topology. We could. Let's discuss it later.
Thank you.
Jarod, less technical point. I think the last thing you wrote on this page should just be 3G minus 3.
Oh, right. Oh my God, I did the same error when I was writing up my notes.
That's okay. Yeah, not as important, but
yeah, it is important to point out because, not everyone might realize it's an error. Okay, now we get to the most challenging part of this lecture, which is the residual gerbes. And I'm sort of regretting that I'm doing it this early. I mean, residual gerbes is a tricky subject, regardless, but it's especially tricky for us because we don't know that much yet. And so there's kind of many ways to show these things, but you'll see that I'm going to struggle because we don't yet have, a lot of the foundation.
Can I ask a question about example 2?
Mm-hmm.
So there was this question about how we can tell that point 0 has one-dimensional tangent space. So is it right to think of these tangent spaces as being like the tangent space as like the tangent complex?
Mm-hmm.
And you kind of forget the grading?
Yeah.
Okay.
Yeah, I think that right. It's sort of the tangent complex is the one that's more well behaved, right?
Okay, cool. So it's like it's a graded one-dimensional thing. Like it has nothing in degree 0, but it's got something in a non-zero degree.
Yeah, yeah. I guess you could. Yeah, right. Yeah.
Okay, cool. Thanks.
Right. So let's first recall what we know about with schemes and what we're really after here. That if X is a scheme, and you have a point, then well, then there exists a residue field K of X, and moreover there's a monomorphism. There's an occlusion from the residue field. And so our goal essentially is like, we want an analogous construction. I mean, it's not going to work out exactly the same way, but we want, yeah. Basically what we want is given X, given a point of an algebraic stack, we want to consider sort of the smallest substack of X containing this point, whatever that means. Right. Okay, and so in fact, okay, so this is, yeah, as I said, tricky. I'm gonna restrict to finite type points. So let me introduce the definition. We say that a point of an algebraic stack is of finite type if there exists a representative such that this morphism is of finite type. And maybe I should point out that a sort of a fact for schemes. If X is a scheme, X being finite type is equivalent to it being locally closed. Closed in some open set. And maybe an example to think of where you have a finite type point that's not actually closed is if you take R to be a DVR, K to be the fraction field, then this inclusion, right? This is an open immersion, so it's certainly finite type, but it's an open point. But for schemes like finite type over a field K, any K point is closed. This is not true for algebraic stacks.
Sorry, could you recall what finite type means in this context? Because it's not a local property, is it?
But it is. Being finite type is a local property. I mean, on the source and target. I mean, we actually define what it means to be finite type for any morphism of algebraic stacks. Here, this map is, we know, in this case, we know this is actually representable. And so you can define, you can just define it in terms of mapping schemes into the target X. and requiring that every fiber product is a finite type algebraic space, where that is, yeah. So we actually have developed what it means for morphisms to be finite type.
Okay, I'll have to read up in the notes, but thank you.
Does the field in this definition, the spec K, does that have to be the same as the one that's just a representative of X, or like?
Oh, wait, in
The
so
point
I
X.
guess so. Yeah, in the definition of an algebraic stack, there's no field. But when I was maybe like here, maybe are you thinking about schemes of finite type over a field?
No, I'm saying, like, you say that a point in the space associated to the stack is a finite type. If there exists a representable arrow from spec K for some field K, I guess.
Oh yeah, this has to be, oh yeah, okay, this is confused. Let me, yeah, I think I too many shortcuts. So yeah, this representable doesn't mean, yeah, okay. If there is a representative of X.
Okay.
Where this morphism is a finite type, yeah. Not that this map is representable. Right, remember we defined the topological space of an algebraic stack to be sort of the equivalence class of all field value points. And here I'm fixing an arbitrary point. There could be many representatives, and being finite type means there's one representative, which is a finite type. It won't be true, of course, that all representatives are a finite type, because you could just take some huge further field extension.
Jarod?
Yeah.
I think one of the confusions is that if the diagonal of X is really bad, then I think you want to say locally of finite type everywhere, right?
Oh, is that, yeah, that's a fair point. Okay.
But and that will maybe clarify what was asked before. And then of course it's a local property both on the source and the target to be locally a finite type.
Yeah. Okay, let me just add that. I mean, yeah. But yeah, I'm going to restrict. I'm going to restrict to X being Noetherian in any case, and then there's no distinction. Then I need to add. Oh, so you can define that. You can also define a finite type point, right? So yeah, if X is Noetherian, then like being locally a finite type. So let me just add this maybe in parentheses, defining two different notions here is equivalent to being finite type. For in this setting of a point. Okay, right, and so, okay, going back over here, like it's useful to keep in mind if you have like a scheme, like a variety defined over a field, then any rational point or any point defined by like a finite field extension is necessarily a closed point. But with algebraic stacks, you can have like these rather benign algebraic stacks like A1 over the complex numbers mod GM, and this point, you have a C point, which is not closed. Right, okay, so now we're going to work towards the definition of a residual gerbe. And right, again, the goal to keep in mind is that we're considering the smallest substack containing X. And we're going to define it in terms of a presentation. So yeah. So let me try to walk you through this definition. So we fix an algebraic stack and a point. And we take a smooth presentation. And then we define the residual gerbe as sort of the substack defined by the stackification of the substacks of objects which factor through your choice of cover here. Does that make sense? Yeah, so, right, you have let me draw a picture. You have U over X, and then you have the inclusion of the residue field. And in the pre-stack, you're forcing, we're trying to define the residual gerb pre, and so that you're forcing like an object, oh no, I used S. An object here, by definition, is something that factors through here. And then what you can show is that, okay, is that if X is Noetherian, this takes some work too, that this is independent of the presentation. So, and maybe, okay. And yet maybe another way to think about this is, you know, if you could choose if you choose a finite type representative, you know, of your stack, like X, then what you really want to do is like, then this thing, GX is sort of like this, is like sort of the stack theoretic image of this map. Like if everything were sheaved, then it would be the sheaf image. So we're sort of taking this to be, yeah, essentially this pre-stack is defined as the pre-stack image, and then we're just sheafifying, stackifying. And what I'd like to show is that, so the following true, so this theorem I've written below, this is true in greater generality than I'm stating here, but I'm imposing, yeah, that one that is Noetherian, and I'm only doing it around points that are a finite type with smooth and affine stabilizer. This makes the argument easier, but you'll see that it still requires some work. This is, and I'll just say in words that this theorem is true. You can look it up in the Stacks project. It's true for arbitrary points without the smoothness and this affineness assumption on the stabilizer. But okay, but the whole point is that this residual gerb is an algebraic stack, and with these hypotheses that it is a locally closed immersion. And moreover, so if I choose a smooth presentation, then the fiber product is exactly sort of the orbit of the corresponding groupoid. Here, let me just explain that this orbit O of U is sort of as sets, it's just this S of T inverse U, which like this is as a set. This is just, if you think about what this is, if you take the pre-image of U under one of these projections T, then what you get is relations that look like V. So yeah, what this is it's all points V such that there exists a relation with source V and target U. So exists this in R. And if you think about it, yeah, if your groupoid came from a group action, this is exactly the orbit under that group action. It's as a set, it's all elements equivalent to U under some relation. And so the sort of the upshot of this theorem is that the orbit is locally closed, so we can give it the reduced. We can give the orbit the reduced scheme structure, as a locally closed subset of U. And I think it's important to compare this with the setting of in equivariant geometry. Like if you have an algebraic group acting on a scheme U, and say everything is a finite type over a field K, then it's sort of one of the first facts you prove in algebraic groups is that any G orbit, at least, yes, say take of a K point, is locally closed. I mean, yeah, the point is that you have this map from G to U, which takes G to G times U, and its image is locally closed. And this is kind of what we're after an analogous fact in a greater generality for stacks. And maybe before going further, let me just give you an example. And I'm going to turn to A1 mod GM. The residual gerb of the open point, whoops, is just is spec K, right? Because that's, yeah. This is an open immersion. And the residual gerb of 0 is BGM. And then if you see what happens under these fiber products, in this case, you just get the origin, but here you're getting A1 minus the origin, right? And these are the two orbits under the A1, under the GM action on A1. And let me just put this in a cloud like Ravi does, because I'm not gonna prove this, but I think it's important to keep in mind is that in general, this residual gerb is a gerb. So I've defined residual gerb, but I haven't defined a gerb. So this is only useful if you know what this means. It's a gerb over a field that we define as the residue field at that point. And so sort of the picture is you have your algebraic stack and you have an inclusion, which is even locally closed if you start at the finite type point. This is a gerb over a field, but it might not be trivial. But if you can take, it is trivial after a tau extensions. So after an tau extension, this becomes trivial, isomorphic to the stabilizer group, maybe of a point X prime. Okay, any questions with the definition? It's probably a lot of questions. It's a confusing construction.
So
Okay,
if I remember
go ahead.
Yeah, so if I remember correctly from your notes, one of the exercises was to show that in general, the notion of in general, you cannot speak of a residue field of a point of an algebraic stack.
Oh, if the exercise is in my notes, you mean?
Yeah, that the generic point like A1 over Z didn't have a residue field.
You can still talk. I mean, well, so there's okay. On one hand, there's this discussion of like what sort of like with weirdly non-separated algebraic spaces or stacks. Okay, maybe some of these constructions don't work, but let's refine ourselves to an Noetherian setting. And in that case, every point, even if it isn't a finite type, every point has both a residual gerb and a residue field. But I'm only going to prove it in a restrictive setting.
Okay, how do you define then the residue field?
Oh, well, I would first define the residual gerb, and the definition I gave is the one that works in general. And then you have to prove that the residual gerb is a gerb over some field, and then that field is defined as the residue field.
Okay, so I take it it's something you don't want to like cover in detail right now.
Right, yeah, I wanted to sort of skip, there's a lot to say here, yeah. And I'm trying,
okay.
Yeah.
All right, so this statement in the cloud then is something that only works in like a nice enough separated situation or something.
Oh, no, I do it sort of, Oh, and now I need to reconnect. No, when I put things in the cloud, it's sort of like when Ravi does it. Sort of, well, it's just meant that I'm doing this for your own edification. This isn't like, yeah, we don't have the background to prove these things rigorously yet, but it's sort of just good to know.
Okay, thank you. I didn't understand the purpose of the cloud. I never attended Ravi's course, sorry.
Do you have an example of a non-trivial residual gerbe?
Oh, I wanted to give one, but I couldn't. Yeah. It's easy. Yeah. I don't really have a great example for that. Yeah. I would like one. I'm sure there is one. I just don't have, yeah.
I guess if you know that there is a non-trivial gerbe over a field, you should get a.
Right. Yeah. But yeah. What's your easiest construction for that? I mean, you could try to take like B of Z mod 2 over, and like try to, take that over the complex numbers and then try to use a non-trivial gluing of that to descend it to spec R. Yeah, that works, but there's, yeah, it's not so easy to state. Okay, so what I want to do is sketch this proof, at least in this special case. And so I've stated again the theorem up there that we're after, and I'm going to prove it in the special case. In the kind of sort of in a geometric case where you have a finite type, where you have an algebraic stack. Remember, it's always assumed Noetherian, and that's imposed further that it's a finite type over a field, and that X is a rational point. So, for instance, this is like, say, take K to be algebraically closed. So if you're working over the complex numbers, this is sufficient to handle it. But and the first step is I want to construct a morphism from the classifying stack of the stabilizer to the stack. And so recall, okay, so I'll hit this, I'll do, well, what is the definition of this? So it's the stackification of the pre-stack where the fiber category at a scheme S, this is simply the category with one object. And where the morphisms between that object are precisely the S-valued points of that group scheme. And so this gives you a way to define a morphism of pre-stacks to X, where the unique object goes to, the corresponding object of the stack X over S. Namely, you just, you take the projection to the spec K and then the inclusion via your point. And then on morphisms, it does, exactly, it just morphisms is defined in the obvious way. So we have this morphism as of pre-stack, so therefore there exists, by the definition of stackification, this map here. And note that this map up here I'll do this, this is a monomorphism of pre-stacks. And what we saw is that, therefore, this is a monomorphism of stacks. So that handles, at least that, So yeah, we get a monomorphism, but we also know that, there's a smooth cover of this, and this map is X. We're assuming this is finite type. So that implies that by descent that this map is also finite type. So now we have a finite type monomorphism, and the goal is to eventually reduce to the case, and we're going to by replacing X by both opens and by closed, and to show that it's an isomorphism. And so in the next step, I'm going to show not only that it's finite type and a monomorphism, but I can reduce to the case where it's flat and surjective. So I can assume that this map has dense image simply by replacing, you simply replace X with the smallest closed substack containing the substack BGX. Okay, and now, okay, this is sense. So if you look at this composition, this has dense image. And this is a representable morphism. And so by descent, by applying generic flatness and applying it, using descent and applying it in the right way, you actually generic flatness implies that this map is generically flat, but it has dense image, and you're mapping from spec K, so it's actually flat. And this implies that the GX is flat. And therefore we're going to use this, and then yeah, so that gives us the flatness, but we also have that it's a finite type. So this map is a flat morphism of Noetherian stacks of finite type. And so you can use descent to prove the familiar fact that flat and finite type morphisms are open, and the image is open. So since the image is open, we just replace X with that, and so we can assume that it's surjective. And so now we finished step 2. We have a finite type monomorphism that's flat and surjective, and now we want to aim to show it's an isomorphism. Okay, so this is the final, with these reductions, I want to show that this is an isomorphism. Okay, and so I have BGX mapping into X, and I have my cover U, and let me just write my hypothesis here. This is finite type, it's a monomorphism, it's surjective, and it's flat. And I simply take the fiber product. I call it O because this is like the orbit of the groupoid. And this, by construction, it's an algebraic stack, but it's also a sheaf. It will turn out, yeah, we don't know that it's an algebraic space. One reason why this argument is tricky. Or a scheme. We don't know yet. Okay, but we can certainly assume that it's local on U. So we can assume U. Let's just assume U is affine. So that but what that tells you is that at least that because U is affine, and this map is this inclusion of O into U has the same properties as bgx into x, this map is finite type, a monomorphism, and flat. And particularly because it's a monomorphism, the diagonal of O inherits the properties from the diagonal of U. And so we at least know that the diagonal of O is affine. This is just a technical thing that we'll use later. And so I'm going to make an assumption here. So let's assume for a moment that we know the following. Let's assume for a moment that we know that O and U are sheaves in the big FPPF topology. A priori, we just know that they're sheaves in the big tau topology. And then now, so we're going to try, because they're sheaves, what I want, and O is a monomorphism inside U, I want to show that they're equivalent as sheaves, that that O to U is an isomorphism of sheaves. And if I use the fact that they're sheaves in the FPPF topology, I just need to show that it's sort of surjective in the FPPF topology. So this tells me that it suffices to show that for all maps T into U, in other words, I have T into U, and I have O here, that I need to show that there exists some T prime, that's FPPF over T, and a lift to O. I need to show I could lift, sections FPPF locally. And I do this sort of, and I can do this sort of in the obvious way. I'm going to do it over here. O to U, I have T. So the first thing I do, remember, this is just an algebraic stack plus sheaf. So I take OT, and then, so because this is an algebraic stack, I choose some cover. So I could choose this to be a scheme, and I could choose this to be, I could even choose a smooth cover. And then I take the further fiber product, O tilde T, and this, let's see if I get this right. U is, T is a scheme, U is a scheme. Oh, and so this is definitely a scheme. And right, this map is smooth and surjective. But we know that this map is flat and surjective. So this composition is FPPF. And so we take T prime to be this lift. So this does show that then O and U are equal as sheaves, and therefore that BGX is isomorphic to X. Wow. Okay. And the one thing I owed you, I don't really want to dwell on it, but I do have this sort of a page explaining this missing fact here. So the missing ingredient is that I'll state this as a theorem that any algebraic space is a sheaf in the FPPF topology. And in fact, if you take the sort of the natural argument for this, just like the argument in Lemon Murray Bailey, you actually see that it extends, like in the case of our setting, to an algebraic stack plus a sheaf, as long as you assume that the diagonal is representable by schemes. And for us, we just reduced immediately to the case of being representable by affine. Here I've sketched the argument, but I'm not going to walk you through it. Maybe we can return to it later if we use it again. But I think it's a good time to end. I'm going to stop the recording.